Tanah pada saat puna padangkan है itu ada ini api itu ada api start करूँ api अभी जब magnetic fields कराने हैं now here we are going to start the magnetic fields. Now magnetic field is occurred by current. Now I think that the magnetic field is generated by the current. Now first thing is how do you find the direction of magnetic field? Now direction of magnetic field is given by right hand law. Now when you keep your fingers, four fingers perpendicular to the direction of thumb. Now when you keep your finger for the direction of your thumb, keep for the direction of current. At that time, other fingers represent the direction of magnetic field. It is very easy to find. Now for an example, you assume this is the direction of current. Now current is I. Now if you want to find the direction of magnetic field in right hand side with respect to the direction of current, now you have to keep your finger like this. In right hand side it goes perpendicular to the sheet, inwards perpendicular to the sheet. Now when you find the direction of magnetic field, left hand side is given by dot. Dot means outwards perpendicular to the sheet. Now this is inwards perpendicular to the sheet, this is outward perpendicular to the sheet. Another example, now we assume current moves right direction like this. Now when you are going to find that the direction of magnetic field above from the current, it is given by, now you have to keep your thumb for the direction of current. Above from the current, now this is the direction of current. Here it gives dot. Now you can see. Now below from the current, it is given by cross. And now this is the summary. When that the current is given by arrow mark, the direction of magnetic field is given by dot or cross. Dot means outwards from the sheet. Cross means inwards perpendicular to the sheet. Now this is the first thing. Direction of magnetic field due to the current is given by right hand law. When you represent the direction of current by the direction of thumb, all other fingers represent direction of magnetic field. Now that is the first thing. Now this is there. Now here we are going to draw the magnetic line by using this theorem. Now everyone write this one in your note. First one, magnetic field is occurred by current. Magnetic field is occurred by current. Next one, direction of magnetic field is given by right hand law. Direction direction of magnetic field is given by right hand law. Now anyway, we will draw the right hand law. Actually, you can draw your right hand like this. You cannot draw your left hand like this. Now this is the direction of current I. So these fingers represents direction of magnetic field. Right? Right. Now right hand law. When thumb and other fingers, when thumb and other fingers keep two perpendicular directions, comma, the direction of thumb represents the direction of current. When direction of thumb represents direction of current, direction of other fingers represent direction of magnetic field. So that this is very important. Listen to me. Now in this theorem only you can change these two values, these two quantities. I mean, if you want to represent the direction of magnetic field by using other fingers, at that time direction of magnetic field is given by direction of thumb. Now I mean you can change these two quantities in this law only. If you want to represent the direction of current by these other fingers, at that time direction of magnetic field is given by direction of thumb. Now you can change it, but generally we use direction of current by direction of thumb, and other fingers represent direction of magnetic field. That is okay, right? Anyway, everyone label the direction of current and then find the direction of magnetic field here and there. Another one, next part. And next one. Then find the direction of magnetic field due to the given current. Now this is I and this is I. Given current is I. Now here you have to label direction of magnetic field for the given current by using right hand law. Right. Now first one. Now you have to keep your direction of your thumb, direction of current like this. the right direction it gives inwards, plus for the leftwards it gives curve. Now here, keep your keep your thumb to the direction of current. So below from the current it gives inwards, plus above from the current it gives outwards dot. Now that is the theorem to find the direction of magnetic field by using the right hand law. Now again last one, keep your thumb for the direction of current like this. Left hand from the current it gives cross inwards perpendicular to the sheet. Right from the current it gives dot. Now that is so. Now this is the method to find the direction of magnetic field by using the current. Now that one is okay. But sometimes they will give you direction of current by dot or plus. Sometimes they will give you direction of current by the dot or plus. At that time you have to find direction of magnetic field. It is given by arrow mark. Now we will see it. Right. Next example. This is the direction of current, so it is given by cross. It is given by cross. Now we are going to find the direction of magnetic field here. Anyway, I will take the first one. You can do it after this example. Right. Now you assume this is the direction of current and we are going to find the direction of magnetic field here. Now everyone keep your finger to the direction of current first and keep your other fingers to the necessary point like this. Now here I mean when the current is given by dot or plus, before finding the direction of magnetic field, draw the perpendicular line with the current wire. Now you can use the right hand law. Now this is the necessary point. So keep your thumb for the direction of current. These other fingers goes right direction. So this is the direction of magnetic field. Now it is very easy to understand. This is the theorem. When the current is given by arrow mark, direction of magnetic field is given by dot or plus. When the direction of current is given by dot or plus, direction of magnetic field given by arrow mark. That is very easy. Next example. Now here you assume. Now we are going to find the direction of magnetic field here. And again, direction of magnetic field you have to find these given points. Now label what are the directions of magnetic field for the given points like this. Now here I told you to draw that perpendicular line with the dotted line first before finding the direction of magnetic field. Then after you can find the direction of magnetic field. Always that magnetic field acts perpendicular to this dotted line. Now for example, here. Now this is the direction of magnetic field. Now keep your thumb to the direction of current. So it gives here perpendicular to the dotted line, like this. Now this is the direction of current, direction of magnetic field. Now you can see. Now these are the direction of magnetic fields. Now when you see it very carefully, now again here I mention the direction of magnetic fields for the given points. But anyway, in this point, it also makes magnetic field. So this is the very important thing. When there is a current, it makes magnetic field around the current wire for one cyclic direction. Now you can see, now this is the clockwise, that is the cyclic direction. Now it makes cyclic direction magnetic line. So when you join these points, it makes cyclic direction magnetic line. So this is the theorem. So now when you have that current inverse perpendicular sheet, it makes clockwise cyclic direction magnetic field. Now you can draw another magnetic line. All the magnetic lines acts like this. Now these are the magnetic line due to the direction of current. Now this is the way how do you draw the direction of magnetic line around the given current wire. Right? Then we will do the next one. So everyone draw the complete magnetic line around the dot. Now this direction of current is given by dot. Now everyone draw the direction of magnetic line around the given wire. Now current is given by dot. Dot means outwards perpendicular to the sheet. Right. Now here this is the theorem. Now you can see it. Now keep your right hand thumb direction up for the given direction. Now this is the dot. I mean outwards perpendicular to the sheet. Now keep your right hand like this. Now you can see this is the cyclic direction around the current wire. Now this is the magnetic line. So that this is the direction of magnetic line. Now this is the cyclic direction. Now you have to put that arrow mark, otherwise they do not take this one as a magnetic line. Now if it is a magnetic line, definitely you have to put the arrow mark. Otherwise that they will not take as the magnetic line. So every time put arrow mark to represent the magnetic line. Now that is okay now? Right. This is the method to find the direction of magnetic lines around the given current wire. I think you can understand it is very easy and it is very easy to understand. Right. Then we will look at the next one. Listen to me. Now, normally magnetic fields we write capital B. Capital B, it says, magnetic field intensity. Now B represents magnetic field intensity or magnetic flux density or magnetic field. Now generally we say capital B magnetic field. Second one magnetic flux density. Third one magnetic field intensity. measured by Tesla. Magnetic flux density or magnetic field intensity or magnetic field is measured by Tesla. Is it okay? Right. So that is okay. Now we are going to draw the magnetic lines diagram for the given two parallel wires. Now write the topic. Magnetic line diagram for the given two parallel wires. For the given two parallel wires. Right. Now you assume these are the given two parallel wires. Right. So that everyone label the cyclic direction of magnetic lines around this right hand side wire as well as the left hand side wire. Now draw it first, then after you can complete the magnetic line diagram. For example, now these are the magnetic lines due to the right hand side wire. Again, it makes another magnetic field by the left hand side wire also. Now everyone put the arrow mark first to represent the magnetic line diagram by using the arrow mark. Now this is the current goes perpendicular to the white sheet. So you have to keep your right hand below to find the direction of arrow mark like this. So it gives clockwise direction. Now you can see it, clockwise direction. Now these are the magnetic lines due to the right hand side wire. Now wire perpendicular to the sheet. Now this is the wire. Now this is the wire. It has inverse current. Now in the left hand side wire, again it has the inverse direction. So it makes magnetic line cyclic direction clockwise like this. Now we have to make, now first of all we have to identify what happened to the midpoint of these two wires, midpoint of given two wires. Now you can see at the midpoint, when you take the midpoint, that right hand side current makes upwards, you can see it. Left hand side wire makes downwards. Now you assume these two current are two identical wires. They have same current. At this point, they have same magnetic field. So the magnetic field is a vector. So it has a direction and magnitude. So now you can see by the left hand side wire makes downwards direction magnetic field and right hand wire makes upwards direction of magnetic field here. Now they have same current, they have same magnetic field. So in this point it makes neutral point. At the midpoint they make neutral point. So that's why when we draw the magnetic line diagram, you do not draw the magnetic lines here. At that time, you have to draw like this. Because at the midpoint of the wires, they do not make magnetic field. Now, this is the theorem. When you have two parallel wires, this is the theorem to draw that magnetic line diagram. At the midpoint, they have no magnetic field. So midpoint, do not draw the magnetic lines. Now here I explain you how does it make a neutral point here. Now that is okay. Now these are the magnetic lines due to the left hand side wire. These are the magnetic lines with the right hand wire. At the midpoint, it has neutral point. So do not draw the magnetic lines here. Now this is the theorem to draw that magnetic diagram between two parallel wires. Uda, everyone write this one. Now write this one. Write this one. At the midpoint of two parallel wires, at the midpoint of two parallel wires with same direction current, magnetic field is zero. At the midpoint of two parallel wires, with the same direction of current, resultant magnetic field equals zero. Resultant magnetic field equals zero. Right. Here I am going to explain what are the characteristics of magnetic lines, what are the properties of magnetic lines. Now we will see what are the properties, what are the characteristics of magnetic lines. Now everyone draw the next topic. Properties of magnetic lines or characteristics of magnetic lines. Right. This is very important. Now you see that magnetic lines or magnetic field due to the current, it makes connected loops. Now in the electric fields of gravitational field, they do not make connected loops. Now you cannot draw circles due to the electric fields of gravitational fields. But this is very important. But in the magnetic field, you can draw complete circles for the magnetic lines. Right. Now here we are going to write what are the properties of magnetic lines. Now write properties of magnetic lines. Properties of magnetic lines. Now, this is very important. Similar electric fields. Now, electric fields or electric lines, they do not have point of intersections. I mean that electric lines, they do not have intersection points. Likewise, magnetic fields also magnetic lines, they do not have intersection point. I mean they do not cut each other. Right, first one, right? Magnetic lines, comma, they do not have intersection points. They do not have intersection points. Next one. Now, generally, these are the common properties. These are the common characteristics of field lines. electric field, magnetic field, gravitational field, all the electric lines, magnetic lines, gravitational lines. If you want to find the direction of magnetic field or electric field or gravitational field, it is given by the tangent at the necessary point. Now, for example, you assume this is the direction of magnetic line or electric line or gravitational line. If you want to find the direction of magnetic field direction, now you better draw the tangent. Now, if you want to find the direction of magnetic field here, draw the tangent first. Now, if you want to find the direction of magnetic field here, draw the tangent at the necessary point. So, always the direction of magnetic field is given by direction of tangent at the necessary point. That is the second problem. Now, write next one. So, that if you want to draw this one, you can draw it like the direction of magnetic field is given by direction of magnetic field is given by direction of tangent. Direction of tangent. Direction of tangent. Now, third one. Now, similarly, in electric fields and gravitational fields, this is the third one. The magnetic line due to the current, it exists up to infinity. I mean, that magnetic field due to the current becomes zero at infinity. It exists up to infinity due to the current. Now, for an example, now you assume this is the current. Now you assume this is the given current. Inverse. Now when you draw the magnetic lines here, you can draw them up to the infinity. I mean, the magnetic field due to the given current exists up to the infinity. Right? Now next one, like this one. Like this one. The magnetic field due to the current exists up to the infinity. The magnetic field due to the current exists up to the infinity. Up to the infinity. Right. So everyone write this one again. Write this one. Now this is the magnetic field. So magnetic field is known as magnetic flux density is known as magnetic field intensity. Now that is measured by Tesla. I will write this one. B, right, magnetic flux density or magnetic field intensity or magnetic field. Then write measured by Tesla, capital T. Measured by Tesla, capital T. Right. Magnetic field is measured by Tesla or magnetic flux density is measured by Tesla. that is okay. Now, here we will move to the next part in magnetic field. Right. Now, this is very important. Now, in the A-level MCQ paper, so many times they will give you like discussion under this theorem. Uh, how do we measure the magnetic field? How do we find the magnitude of magnetic field by using an equation? Now, first one. Now, this is mu naught. Actually, you have done everyone. You have done the friction force lesson of frictional force. At that time, we define that mu. That's the coefficient of friction. Coefficient of friction of dynamic force, coefficient of friction static. Now, at the friction mechanics lesson, that mu represents coefficient of friction. But in the magnetic field lesson, this mu represents permeability. 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 Permeability, it represents the strongness of magnetic field at a point. It represents what is the magnetic field magnitude. Now, it is the factor of magnetic field. It represents the strongness of magnetic field. Now, that is called permeability. But when you draw mu naught, when you write mu naught, that is permeability of free space or air. Now, mu naught represents permeability of free space or air. For example, in the electric field lesson, you have done this one. Electric field is written by 1045 epsilon naught q divided by r square. Now, this is the general expression. This is the general expression for the electric field by the static charge q at distance r. Right. Now, this is the general expression for to find the electric field for the static charge q at distance r. Now, that is okay. In this equation, we write epsilon naught. So, this is permeability. That is permeability. That is a factor of electric field strongness. Similarly, and this is the permeability of free space or air. Now here, mu naught, that is the permeability of free space or air. That is the factor of magnetic flux density or magnetic flux strongness. Permeability. Mu naught means permeability of free space or air. That's it. Right. Write the next topic. Write the next topic. The direction of magnetic field due to the direction of magnetic field due to the connected loop. Due to the connected loop. the direction of magnetic field due to the connected loop. Now here we are going to label the direction of magnetic field due to the ring. Now for example, now assume the plane of ring parallel to the vertical direction like this. Now this is the ring. This is the ring. It carries current I. Now this is the current. Now here we are going to label the direction of magnetic field at the center of the loop. Now assume that the loop parallel to the vertical direction like this. Vertical direction like this. For example, that ring exists like this, parallel to the vertical direction. Now here we are going to label the direction of magnetic field at this center. Now this is the ring. Always when the current is given by arrow mark, direction of magnetic field is given by dot opposite. But here, listen to me. Now this is the direction of current. You have to keep your thumb to the direction of current like this. Now you can see that center place in front of the current like this. So you have to keep your finger like this. At that time, it makes magnetic field like this. Now this is the direction of magnetic field due to the current. Another example. Now you assume the plane of connected loop parallel to the horizontal direction. Plane of connected loop parallel to the horizontal direction. Now you assume it has current for the given direction like this. Now this is the cyclic direction of current. It exists parallel with horizontal direction like this. Now we are going to find the direction of magnetic field at the center. Here. Now, first of all, everyone keep your thumb for the direction of current like this. Now, always the direction of magnetic field perpendicular to the plane of circle. Now, this is the plane of circle horizontally. So, direction of magnetic field perpendicular to the circle. Plane of circle like this. Now you can find the direction. Now keep your thumb on the current direction and keep your other fingers for the necessary direction. Now center place in front of the current like this. So magnetic field acts here. Now this is the given current. Now this is the direction of magnetic field. So this is the much more important thing. When there is a connected loop, always direction of magnetic field perpendicular to the plane of flow. Now here, plane of flow vertical, direction of magnetic field horizontal. Plane of flow horizontal, direction of magnetic field vertical. That is the method to find the direction of magnetic field when you have connected loop. So everyone draw these two diagrams, then I will tell you what is an art. Now first one, everyone draw these two diagrams first. Sometimes they will give you two perpendicular connected loops. At that time also we have to find the direction of current at the center. But anyway, I teach to how do you find it? Now everyone write this note. Write this note. Of magnetic field due to the connected lobe. The direction of magnetic field due to the connected lobe. Direction of magnetic field within brackets center. The direction of magnetic field at center due to the connected lobe. Always perpendicular to the plane of lobe. Always perpendicular to the plane of lobe. You can see it. Right. Now we are going to find the direction of magnetic field when the system has two concentric lobes. Two concentric identical lobes. Now here we are going to find what is the resultant magnetic field direction. Now these are the two concentric connected lobes. Now first lobe parallel to the horizontal direction like this. Second lobe parallel to the first lobe parallel to the vertical direction. Second lobe parallel to the horizontal direction like this. Now you assume these two concentric wires have, now these are the two concentric circles. Now they have current, same identical current. Now we are going to find the direction of magnetic field here. Now you assume these are two perpendicular concentric lobes. Now everyone draw this one first. Right. Now here we are. Now first of all, keep your mind. This is very important. Magnetic field is a vector. So when you have two vectors, at that time you have to simplify them as a vector simplification. You cannot simplify them as algebra. Now definitely you have to simplify them as a vector simplification. Now everyone knows what are the vector simplifications. When two vectors are perpendicular with each other, at that time resultant vector is given by Pythagoras theorem. Now everyone knows this one. Now when two vectors are perpendicular with each other, at that time resultant value is given by the Pythagoras theorem. Right. Now here, first step. Right. Everyone mention the direction of magnetic line due to the vertical loop first or horizontal loop first as you wish. Now here I am going to label the direction of magnetic field due to the vertical loop first. Everyone knows this one how to label it. Now this is the direction of magnetic field due to the vertical loop B1. Right. Now again everyone label at center direction of magnetic field due to the horizontal loop circle. Now this is the horizontal loop. Now here I give direction of current like this, so it makes downwards because I told you always the direction of magnetic field at center due to the connected loop perpendicular to the plane of loop. Now vertical plane, perpendicular plane plane means horizontal. Now second one, horizontal plane lobe, perpendicular direction means vertical. Now here anyway, we have to use right hand lobe to find the direction of magnetic field properly. It makes downwards. Now that is downwards. Now here, now listen to me, Buddha. This is the B1. It represents magnetic field due to the vertical lobe. This is the magnetic field due to the horizontal lobe. Actually, they have equal magnitude, equal values due to these two identical currents. But here, I label B1 and B2. It is very easy to identify what is the vertical and what is the horizontal. But anyway, when they have same current with the same loop, identical loops, these magnitude of magnetic fields are also equal with each other. Right. Now anyway, I label B1 and B2. Right. Now at the center, it has two magnetic fields. So magnetic fields are vectors. So you have to find this is resultant magnetic field by using the Pythagoras theorem. Now B1 here, B2 here. So resultant magnetic is given by. Now this is the resultant magnetic field at center. It is given by B1 square plus B2 square 2. Now this is the theorem to find that resultant magnetic field when you have concentric two circular planes. So you have to use the Pythagoras theorem to find the direction of magnetic field to find the finite center. Now this is the theorem. It is very easy. Now this is the magnitude. Magnitude is given by Pythagoras theorem. Now if you want to find the direction, now it is given by tan theta. Now everyone knows two perpendicular vectors are perpendicular. Magnitude is given by Pythagoras theorem. Direction is given by tan theta. Now if you label the theta here, direction tan theta is given by opposite side is B1 and adjacent side is B2. And theta is given by tan inverse B1 divided by B2. But here, this is not important in magnetic field because these parts are considered in mechanics. Now in magnetic field, always we find the magnitude of magnetic fields only. They will not ask you what is the direction like these questions. Right. Now write this knot. When two perpendicular circular loops, circular concentric loops are in the system, the magnitude of magnetic field is given by Pythagoras theorem. Magnitude of magnetic field is given by Pythagoras theorem. Now this is the way to find that direction of magnetic field. Right? Is that okay? That is very clear. Now always direction of magnetic field is given by right hand law, and when you have two concentric loops, at that time you have to find one by one first. Then after you have to use Pythagoras theorem to find the magnitude. That is all. Right. Would everyone draw the horizontal line again? Right. Now listen to me. Now here we are going to the equations to find the magnitude of magnetic flux density or magnetic field intensity, because the magnetic flux density is known as magnetic field or magnetic field intensity. All are represented by capital T, capital D. All are measured by Tesla. Now we are moving to the equations in magnetic fields. Now listen to me. Now this is the Biot-Savart law. Now before the Biot-Savart law, I will tell what are the equations first, because that in the we do not apply that Biot-Savart law to find the magnetic flux density. That's only just a law. That's it. But here we will move the equations first. Then after I will explain what's the Biot-Savart law. Right, because all these equations are formed by the Biot-Savart law. So in the A syllabus, it has Biot-Savart law, but we do not apply to find the magnitude of magnetic field by using Biot-Savart law, because all the applications are done by given these three equations. Right. Now this is the theorem. Always magnetic field is generated by I naught. So when you write the equation, be directly proportional to the I. So always I comes up above from the line. Now everyone knows when you travel away from the magnet, so it decreases the magnitude of B. So we assume there is a magnet here and you run away from the magnet. At that time you feel the magnetic field gradually decreasing, because that distance gradually increasing. Now you can take the idea. Now always distance inversely proportional to the B. Now all the equations in magnetic field, I exist upon the line because that magnetic field is generated by current, and again magnetic field inversely proportional to distance. So all the equations in magnetic field, I should be here and R should be below from the line. Now that's the first thing. Now second thing is, there should be a constant value here. For example, when you write force in electric field, you write 1045 epsilon naught Q1 Q2 divided by R square. E 1045 epsilon naught Q divided by R square. Now again, if I write that V, electric potential due to static charge, also given by 1045 epsilon naught Q divided by R. Now you can see each and every equation in an electric field, it has this constant 1045 epsilon naught. Similarly, when you write an equation for magnetic field, at that time also in each and every equation, it has constant. That constant is mu naught divided by 4 phi. Right. Now, listen to me. That is very easy. In all equations in magnetic field, there should be a constant. That constant is mu naught divided by 4 phi. Actually, this value is 10 to the power minus 7. Now, they will give you that value. Mu naught divided by 4 phi. Now this is the constant value in all equations in magnetic field. Right. Always magnetic field is generated by I. So capital I comes here upon the line. Always magnetic field decreases by distance. So R comes down. I mean magnetic field inversely proportional to the distance, and magnetic field directly proportional to I. In all equation in the magnetic field, this constant, come on please, now that is solved. Now here I will explain how do you form the equation, how do you take the equation. Now three equations are in the magnetic field, that is much more important in the A level. Now, for an example, now here I will explain you how do we take that equations first, right? So the first one, magnetic field due to the current. Now, current exists both sides from the considered direction. Now here we are going to find the magnetic field at point here. This is R. Right. This is the second one. Now in this case, the current exists both sides with respect to the point of magnetic field. Now this is the necessary point. Now you can see current exists both sides from the necessary point. That is first one. Second one, current exists in one side from the necessary point. Now you can see this is the current, this is the current, and this is the distance R, and this is the necessary point. This is the point which you are going to find the magnetic field. Right, next one. When the wire is bended like this, now this is the center. Now we assume subtended angle at center as theta. Now this is the current. Now this is the necessary point. Now in the A level, we are going to write this magnetic field B for these three cases. So now in the A level exam, the MCQ paper, definitely they will ask you the application by using these three equations. First one, when the current exists both sides from the necessary point. Second one, when the current exists one direction from the necessary point. Third one, when the wire is bended and assume subtended angle center theta. Right. This is very easy. First one, now here I am going to write the first equation. Right? First equation, B equals, I told you always it gives mu naught divided by 4 pi. Always it has I and always it has R. In this equation, always it has mu naught divided by 4 pi. Always it has I and R. So the always it has mu naught divided by 4 pi and I divided by R. Right. Now there are very small thing to understand this one. When it exists both sides from the necessary point, multiply this equation by 2. When the current exists one side from the necessary point, you have to multiply this 1. Actually, no need to write that 1, no? So we do not write 1 here. Next one, third one, when the wire is bended, mu naught divided by 4 pi, I divided by R. If it subtended angle at center theta, you multiply by theta. But anyway, this is very important. Theta should be measured by radian, not with the degrees. For an example, 108 degrees means radian 5. Now these are the three equations. Now here I am going to explain these three equations again. Always it has mu naught divided by 5, I divided by R, mu naught divided by 4 pi, I divided by R, mu naught divided by 4 pi, I divided by R. When the current exists, both sides from the necessary point, you have to multiply by 2. When the current exists, one direction from the necessary point, you have to multiply by 1 when the current exists or when the subtended angle at center theta, you have to multiply by theta. Now listen to me. Now anyway, here I am going to draw these three figures in one row like this. Huh? So it is very easy to take the note. Right. First one, when the current exists both sides from the necessary point I. Now this is the next one. When the current exists one side from the necessary point, this is side, this is R. Next one, when the wire is bended, subtended diagonal at center theta, I, radius is R. Now this is the B. Right. So that now everyone knows how do you find the direction of magnetic field here. So it is given by cross. Now this is the theorem to find that direction of magnetic field by using the right hand law. Now that is okay. Now in this time also it is cross, because when you use the right hand law to find the direction of magnetic field, it is given by cross. Now this is the next theorem. Now this is inverse. This also cross. Now that is okay. Now again we are going to find three equations here. Right. So here in all equations mu naught divided by 4 phi, I divided by r should be here. Mu naught divided by 4 phi, I divided by r should be here. Mu naught divided by 4 phi, I divided by r here. It is very easy to understand and keep your memory. Always magnetic field is generated by current and it is inversely proportional to R. Right. Now when it exists both sides, when the current exists both sides should be multiplied by 2. This should be 2. When we exist in one side, should be multiplied by 1. No need to write it. When it makes theta at the center, should be multiplied by theta. So these are the three equations. These are the three equations in the error. Definitely, they will ask the question to find the magnitude of magnetic field by giving these three equations in the error. Normally, generally, they will ask you, every year they ask, what's the magnitude of magnetic field here? By using these three equations. Right. Now, everyone take the note. Here, everyone write in first diagram, when the current exists both sides from the necessary side. In the second diagram, when the current exists one side from the necessary point. In the third diagram, when wire is bended. When wire is bended. Now then write the four equations and highlight them. सामान्य में अपने मैट्रिक फेल्स कराती और मुली මුලින් මේව equations සයින් එක කියලා එහෙම හිතනවා. ඒකට applications කරන්න මේක nothing. ඇතිම දෙයක් නෑ පුතා. කරද්දී මේක application එකක් දෙයක් කරද්දී අයියෝ මේක කියලා හිතනවා. ඒ මට්ටමට එන්න ඕනේ නැහැ. Right. Buddha, listen to me. Now this is the very first application. Buddha, this is I and this is right angle. Now this is the given connected lobe. Now here we are going to find magnetic field at center. Right. Buddha, this is the theorem. Along the given current line, it does not make magnetic field. Buddha, now this center exists along this current line, wire line, so this part does not make magnetic field. Right, Buddha? Again, now we are going to find the magnetic field at center. Now here, when the necessary point exists along the current line, or when you extend that line, when it necessary point lies along the extended line, it does not make magnetic field. Buddha, here you can see we are going to find magnetic field at center. So this is the current line and necessary point exists along the current line. So this current does not make magnetic field at center. So again, this current does not make magnetic field at center. That is the first thing. Again, when you extend that given line, current line, when the necessary point exists along the current line, at that time, current does not make the magnetic field. පුතා දැන් මේ ලයින් එක උඩනේ මෙයා ඉන්නේ මේ කරන්ට් ලයින් එක මෙතන මෙයා හදන්නේ මේ ලයින් එක උඩනේ පුතා මෙයා ඉන්නේ මෙයා හදන්නේ but you can see this line when you extend this line like this you cannot meet that necessary point so it makes the magnetic field at center that is very easy now first thing these two lines do not make magnetic field at center because that center exists on these two current lines. උදා මෙහෙමද? මේ වයර් එක දික් කරනකොට ඒ ලයින් එක පොයින්ට් එක හම්බුනත් ඒ පොයින්ට් එකේ කරන්ට් මේ magnetic field එක එකකින් හැදෙන්නේ. ඒ හිතන්නකො වයර් එක තියනවා පුතා මේක. වයර් එක දික් කරගෙන යනවා. දික් කරගෙන යනකොට අපිට necessary point එක හම්බුනවා. එතකොට අපිට magnetic field එක හදන්න. Now when you take these two lines and this is the necessary point, now necessary point lies on these two lines. So they do not make the magnetic field at center. Now if you extend this line, you can see that necessary point you cannot meet it. So this curved line, only this curved line makes the magnetic field at center. Right. Now we are going to write the value. Now everyone knows when the wire is bended, it is written by mu naught divided by 4 phi I theta divided by r. But here I told you theta is measured by radian. Everyone knows that theta equals 90. 90 means 5 divided by 2. So you have to apply 5 divided by 2 here. Then the answer is given by, you have to apply 5 divided by 2 here. That is very easy. And again find the direction. Now keep your finger thumb for the correct direction like this. Make plus. Now this is the value. Right. Could everyone do this one? Now if you want to write this one, you can write as mu naught divided by 8 phi I divided by r. But all it simplified. First of all, understand how do you find it? How do you calculate this? Is it okay? Now this is the very first application. Kita amme ke kahalan. Meka harina lesi kita. Eka burukata amaru karaganne pa. Nothing. Equations na kisse mera kita burukata dagana harina lesi. Mu naught पे मात्रा है फाइव हुआ. हम equations फाइव की बात की. उन्हें एक के हुआ. Mu naught फाइव by फोर फाइव हुआ. हम एक फाइव by हम एक के सेंटर के थीटा रिपोर्ट थीटा मेथड का. इधर थीटा जानना है रेडियस. इच्छा है. ඊට පස්සේ පුතා වයර් එක දික් කරනකොට වයර් එක දික් කරනකොට අපේ necessary point එක හම්බ වෙනවා නම් ඒ වයර් කෑල්ලෙන් පුතා එතන magnetic field එක හදන්නේ නැහැ. දැන් මේ වයර් එක දික් කරනකොට පුතා center එක හම්බ වෙනවා. ඒතර මේ කෑල්ලෙන් හදන්නේ නැහැ අපරදා. මේක දික් කරනකොට පුතා මෙතන හම්බ වෙන්නේ නැහැ අපරදා. Is okay? Right. Next one. Right. The applications they are going to make code right. Now we will move the next application. So listen to me again and again. When you extend the line, when the necessary point exists on the line, at that time that bar never makes the magnetic field. Right? अब wire के extend करना पड़ता पुता necessary point के हम बिना ना या एक magnetic field के इतना हलन में हरिයට පුතාලගේ බර පුතාලට දැනෙන්නේ ඒ වගේ line එක උඩ current line එක උඩ magnetic field එක හැදෙන්නේ right. Now we will put the next example na right. Right. Now radius is r and current is I. Now here you have write B. Put everyone write value for B. Then I will explain. Before the explanation, everyone do this one. Now first of all, everyone you have to understand. You have to decide what current, what wires make that magnetic field at center. Then after write the correct equation. Always, if it is bended, theta should be written by radian. 180 equals 5. 90 equals 5 divided by 2. 45 equals 5 divided by 4. Like that. Right. Now enough time. Now again I explain you. Right. Now you can see. Now this is the necessary point. This is the necessary point. Now when you extend this line, you meet that necessary point. So this part does not make the magnetic field at center. This part does not make magnetic field at center. Because when you extend this line, you can meet that necessary point. Again, when you extend this line, necessary point on that line, so again it does not make magnetic field. Now you can see, when you extend this line continuously, so you cannot meet that necessary point, so it makes the magnetic field at center. So everyone knows that equation. Equation is B equals mu naught divided by 4 phi I theta divided by r. Theta means 180 degrees here, 180 means phi in radian. Now this should be the answer. Check whether it is correct. Now everyone, you have find the direction also. Direction. Now keep your thumb for the current direction here and check the direction of magnetic field at center like this. So it gives plus. It gives plus. That's it. That's it. It is very, very easy. Right. Put everyone before the next application. Actually, now you can do that next application with your answer. But anyway, I'll do the knot, very small knot, to understand this one. So everyone write this one. When extend the current line, comma, if the necessary point lies on extended line, extended line, it does not make B. Right. Right. Then we will move to the next one. Next application. Now everyone you can do it. Right. Everyone draw this one. Now this radius is A and this radius is B. Current goes like this. Now everyone label the magnitude of magnetic field at center. Draw the given diagram first. Everyone send me a message just after this application because I want to understand how to fill this one. So everyone send me a message after this application. Because I want to understand what to feel like. So everyone send me a message just after this application. Listen to me first. Now, first of all, everyone cut the unnecessary current wires first. Now we are going to find the magnetic field here. Now when you extend this line, you can make that necessary point. So this part does not make magnetic field at it. Similarly, when you extend this line, again it does not make magnetic field because you meet this line at the center. Now you can see two wires, these two curved wires make magnetic field at center. Uta, listen to me. This is the shortest path to find it. Uta, you can see these two current directions are opposite with each other. When they are opposite with each other, they make opposite direction magnetic fields. So these two wires make magnetic field here, but they are opposite with each other. So when you take the resultant value, definitely you have to take the subtraction. Take mu naught divided by 4 phi in front of the bracket. Now listen to me, Puta. Listen to me. Always closer wire makes larger magnetic field. When the wire is close to our necessary point, it makes the larger magnetic field. When the wire is at far, it makes low magnetic field. Because magnetic field inversely proportional to distance. Puta, this is the method to label direction of magnetic field. When you have two opposite direction current wires, always direction takes near magnetic field, near line magnetic field, near current magnetic field. Now you can see these two current make magnetic field center, but near wire see here. Now near wire makes magnetic field cross. Outer wire makes dot, but near wire makes larger one. So direction is cross. Now you have to write the proper equation here. Now everyone they have bended. It makes I theta divided by r. So everyone you have to understand what is that summation or subtraction. Then everyone write it. Then after I will explain it again. Mu naught divided by 4 pi is a common factor. Take mu naught divided by 4 pi as a common factor in front of brackets. උදාර පොඩි ළමයි වගේ ගණන් හදන්න එපා. උදා හැමතිස්සෙම shortest path වලින් ගණන් වලට යන්න ඕනේ. ගණන් වල ගන්න එක මට්ටමකට ඇඩ්වාන්ස් වෙන්න ඕනේ. එතනින් පල්ලෙහාට උතා බෑ. එතනින් පල්ලෙහාට ඒවල් කරුවට කෙරෙන්නේ නැහැ නේද? නිසා එතනින් මට්ටමට මේ ඇඩ්වාන්ස් මට්ටමට යන්න. very first day තමයි මේ අවශ්‍යතාවය යන්න. Right? Now here I am going to write the value. Right? Now radius A makes mu naught divided by 4 phi I theta divided by r. Theta means phi. R means A. Now this is the magnetic field due to inner current. And this is the magnetic field due to outer current. Mu naught 4 phi I theta also phi divided by t. But here they make opposite direction magnetic field. We have to take subtraction. That's only you can simplify it after this one. But anyway, I want to write this one. Right? Could everyone send me a message now? Everyone send me a message just before the next application. Could a simplification very not get a message you understand? ඒවා පුතා වැඩක් නැහැ simplifications very not කියලා. පුතා මේ theorem මේ කාර්ය කියන එක. නැත්තම් පුතා ඒ මට message එකක් ටක් කරන්න. Is that correct or wrong? And okay, if it is okay, you just write okay. I got it. Now you are okay. Right. Actually, this is a Sri Lankan level past paper. So that later, if you can understand this one, you can go ahead without any difficulty. Without any difficulty. Right. Right. We are moving to the next application. We are moving to the next application. Right. Right. To the next application. To the no need to be hurry. Now, first of all, we have to identify the given question. Then after, extend the line. Just after, then after, you can understand what is the magnitude of magnetic field. Right. Now, this is clear. Now, this is a given question. Right. Now, these are identical parts. Now, this is the arc of circle. Here I cannot write it properly, but anyway you can understand this is the circle, and this is I, and this is the center B, and this is I. So everyone write the question. Find the magnetic field at center. Find the magnetic field at center. So that then we'll see it now. Now everyone write the values after this expression and simplify it. Now finally everyone write the final value just after the final simplification. Right. Here I am going to simplify it. I am going to explain it first. Right. So these are two identical parts of upper parts and below parts are equal with each other. So they have same resistance. When upper part and below part difference in each other, that resistance depends on the length. So larger length has small current, small length has larger current in resistance wise. But here you can see these two wires length, upper part and below part length are equal with each other. So they have same current. But when you come here, the total current is I. So it distributes that I for the upper part and below part equal with each other. So when you label the magnitude of current for the given two parts, I divide by 2, I divide by 2. That is very easy to understand. So I comes here, we have to divide it both parts. Now find it both parts are equal with each other or identical. If the parts are identical, you have to divide current with same portions. So I comes here, I divide by 2, I divide by 2. Now you have 4 current wires. First one, second one, third one, fourth one. Now we are going to find that B at center. Right? Now here again you can see when you extend this line, you meet that B. When you extend this line, you meet that B. So they do not make magnetic field at center. They do not make magnetic field at center. Right? To the next one, these two wires make magnetic field at center. They have same current. They have same angle at the center. And again find by using right hand law, how does it make magnetic field at center? Then everyone write the total magnetic field at center. Right. Now everyone do this one. Then simplify it. Then write the final answer. Actually, no need to find it. Now you can see, now listen to me, then we will calculate it second. Now first everyone find it like this. Now they have same current. Now general expression is u naught divided by 4 5 I theta divided by r naught, right? Now do not simplify it. Now everyone knows this value is common. That is common value. That is constant. Upper part and below part, now they have same current. I is same. Upper part and below part, they have same radius. R also same. Upper part and below part, they subtended angle at center 180. Theta also same. But they make different directions. Upper part makes cross, below part makes dot. Now you can see, now this is the upper part, it makes center cross. Now use the right arrow, it makes center cross. Below part, it makes center dot. So they make same and opposite, same magnitude with the opposite direction magnetic field. The magnetic field is a vector. Now you have same and same in magnitude but opposite in directions. So total value is 0. If you simplify it by using the equation, now here I am going to write this by using the equation. But actually you can do it by using like this. No need to write the equations. If you can understand, upper part I theta divided by r theta phi, I theta divided by r theta phi. Now this is the upper part and below part. Now this is upper part plus below part. Now you can cut them as is 0. Now everyone do this one as a homework. Make a mema, right? Mema ගෙදරදී කරලා බලන්න. Now everyone do this one as a homework. මෙතනදී මෙහෙමාවක් මේ කැලි අනිවාර්යෙන් 0 වෙලා යනවා. ගෙදරදී කරලා බලන්න. ගෙදරදී කරලා බලන්න. හැබැයි පුතා ප්‍රශ්නේ මේ වයර් එක දික් වෙනකොට ඒකේ කරන්ට් එක අඩුයි. වයර් එක කෙටි වෙනකොට කරන්ට් එක වැඩි. දැන් මේ කරන්ට් එක 3ක් මේකයි වුණොත් මේක 3යි. හේතුව පුතා දිග නම් රෙසිස්ටන්ස් එක වැඩි, කරන්ට් එක අඩුයි. But we will check all these things next part. Right? Now that is over. Now this is the summary. Now this is summary. Now this is the summary. The first one, the direction of magnetic field due to the current is given by right hand law. Is given by right hand law. Is given by right hand law. Right? Second one, always when you take the current around the current wire, it means cyclic direction. It also given by right hand law. Next one, we have three general expressions to find. Equations to find that magnetic field by using three equations. Those are, first one, when the necessary point here, when the current exists both sides from the necessary point, that D is given by mu naught divided by 4 phi. Now I will write it there after draw this one. Now next one, when the current exists one side from the necessary point, next one, when the wire is bent, subtended angle theta, B. Now always mu naught divided by 4 phi exists here. mu naught divided by 4 5. All the equations in magnetic field, they have mu naught divided by 4 5. Always I and R here, because B is generated by I out from the line and R inverse the B. So when the current exists both sides from the necessary point, you have to multiply by 2, multiply by 2. When the current exists in one side, you have to multiply by 1, only divide by 1. When it makes t times center, you have to multiply by 2. But theta should be measured in radian. That's it. Now these are the three equations. These are the three equations in magnetic fields. This is the first part. Then we will next part. We will go to the next part in next week. Right. Okay then. උදාහරණයක් ඔයගොල්ලෝ මේ magnetic fields වල මේ කොටස් හරියට ලේසි. බොරුවට අමාරු කරගන්න එපා. මෙන්න මේ කරපු ටික විතරක් ආයෙ කරන්න. right hand row එක දාන්න මේ equations තුන පොඩ්ඩක් ලියන්න. equations තුනේ මොකට ආකාර කියලා පුතා. අපි මේ applications ගොඩක් කරනවා. ඒකට මේක බලන්න පුළුවන්. right. right. එහෙනම් පුතා අපිට නවත්තමු මේ පුතාලා ඔයගොල්ලෝ පොඩ්ඩක් comments එකක් දාන්න මොකද කියලා වැඩේ. මට මේක අර ඔයගොල්ලෝ online වලට විතරක් සීමා කරලා තියන්න බෑ වැඩේ. මට ක්ලික් වෙන්න ඕනේ. පුතා ඔයගොල්ලන්ට හරියට check වුණාද නැද්ද කියලා මොකද මේ පාරේ exam කියන්නේ. ඒ නිසා පුතා ඔයගොල්ලෝ මට මේ comments එකක් දාන්න මොකද කියලා. ඒතර වගේ වගේ බලන්න නම් ඊට පස්සේ පුතා දැන් මගේ physical class එන අය පුතා මේ අනිවාර්යයෙන් මේ හෙට උදේ අපි ඩිස්කස් කරගත්ත පුතා ක්ලාස් එක තියෙනවා කියලා. හෙට උදේ අපි නැති කරමු. හෙට උදේ නැහැ. හෙට ඉංග්‍රීසි මීඩියම් ක්ලාස් එක උදේ ඉලෙක්ට්‍රික් ෆීල්ඩ්ස්. හෙට නැහැ පුතා අපි ඊළඟ දවසේ තියමු. එතකොට මේ මාස ඉවරේනවා අපේ ඉලෙක්ට්‍රික් ෆීල්ඩ්ස් එතනින්. එතකොට අපිට ඒ වැඩි කරගන්න පුළුවන්. right. පුතා right, say good night. Everyone send me a message. Okay then. So good night පුතා.